And let's now look at a different kind of problem, but related to the confidence interval that estimates the value of a population proportion. And I put that kind of a problem in example 2 here. So let's spend some time reading our example 2. The true proportion of iPhone users. So this true proportion here is that population proportion right here. So once again, the true proportion of iPhone users is estimated to be in anywhere from 0.7485 less than p less than 0.7715, and this interval is at 99% confidence level. How large must the sample be to ensure this estimate? And so ultimately, as a goal, we are not looking for the interval. So let's look at the very ending question right here. How large must the sample be? Or this should have been, how large must a sample be to ensure this estimate? So what does this mean by how large must the sample or a sample be to ensure this estimate? The idea is we already had an estimate given in our problem. So we estimated that our true proportion, our population proportion of iPhone users globally is known to be in this interval. So this triple-sided, this three-sided inequality here is indicating that our value, the true proportion of iPhone users, is being inside of this low end right here, and this high end is here. Further, this interval is guaranteed at 99% confidence level. And so we want to find out how large must the sample be to ensure this estimate. So let's understand the problem a little further right here. But so what we know here is that, so as far as known or given information, so what we know is that our p-value, our true proportion value, is happening anywhere between 0.7485 and 0.7715. And so in a different way of understanding this inequality, it means our p-value, our true population proportion value is estimated inside of this interval right here. So 0.7485, and the high end is 0.7715. So this is our, in other words, this is our confidence interval already given. And we already knew from our beginning description of the problem that our interval here is a 99% confidence interval. And so in that way, our confidence level here is being 99%. So C equals 99. And for computational use, I am going to put this in a decimal, 0.99. And so that is the given information. So here in this problem, looking back on my screen again, but the question is actually asking how large must the sample be. So as a question, then we are trying to find out how big that capital N, the sample size, how big does it need to be? Because remind yourself, so this is what we need as a reminder right here. But after we've learned how to find or how to construct the intervals, any of these intervals, any of these confidence intervals, then the way it's done ultimately is we need to find a sample proportion. And from that sample proportion value, we were finding, as the next thing, the margin of error to figure out how far up and down from where our sample was. We've learned from experience doing past examples that changing the sample size will change, or in here I'm saying changes the margin of error. So this is one quite important understanding that we have drawn through past examples. Further, we've also learned that the larger the sample size is, the smaller and necessarily the better, the more accurate margin of error we can get or will get. And so now here is how we start. So once again, any confidence interval, known or unknown, is in the format of taking some p hat, some sample proportion value to be in the middle of the interval. And low and high end of the interval come out by adding or subtracting a margin of error. And so the way, and I also made this illustration back in our earlier videos about how we find the confidence interval. But so in this way, we can think of the interval as having p hat exactly in the middle, and low end is here, and high end is here. So this low end comes out from p hat minus the margin of error, and this high end comes out from p hat plus the margin of error. So that's how it has been. So now in this particular case, since we already had a known interval, then that means this low end here, yes, it comes out from our p hat, subtract the margin of error, and we don't know any of these yet. We don't know what p hat is, we don't know what margin of error is, but we actually already knew that our low end in this case is 0.7485. And for the high end, as a reminder again, we still don't know the values of the sample proportion and the margin of error, but we already knew that the high end is 7715. So at this point, anyone viewing this video is starting to have a plan in mind. The margin of error, as I have already explained in here, I'll explain again, but the margin of error, in other words, the margin of error is simply the distance from p hat, the sample value right in the middle, to either end of the interval. So in other words, from p hat to the upper end to the high end, it's that margin of error, or it's the same distance from p hat out to the lower end. So that means, in other way of saying, margin of error in the way how I'm drawing my picture here is half the distance, the total distance of the interval, or half of the total length of the interval. That gives us a clue how to come up with the value of margin of error. So in this case, in this problem, we cannot calculate the margin of error using the formula. Remind yourself. Margin of error, we used to have the formula z sub c multiplied with square root of p hat times 1 minus p hat over n. But unfortunately, this formula is not going to be applicable in this problem due to the fact that we do not know what that p hat value is. We don't know what the sample size is, and as a matter of fact, that is what we are trying to find out. Z sub c we can calculate because we already had a confidence level, but in the end we're having a lot of missing information here. So to make clear with my point again, we are not able to proceed using this formula to calculate margin of error. And so in that way, here's how I can still figure out the margin of error using the information we've had. So back to the description I've had here, here's the low end, here's the high end of the interval. In that way, how the picture is written, then we're looking at, let's find the total interval's length here first. And that total interval's length, the famous and the only math of getting length is 0.7715, the high end of the interval. And we're now subtracting 0.7485, the low end of the interval. And that length as a difference is the length of the entire interval, as a reminder. But the margin of error is not the entire length of the interval, the margin of error according to the picture is only half of the length. And so I am going to take that difference and divide it by 2. And so final calculation comes out to be 0.0115. And so now all of a sudden we realized that even though we completely bypassed using the formula, but we were still able to find out how big our margin of error was. And so now once we've had margin of error, think about one more time. Let's look back at the formula, the formal formula for finding margin of error. So margin of error equals z sub c. We can calculate z sub c easily. So I'm holding that for another steps right here. But z sub c times the square root of p hat 1 minus p hat over n. We already had this margin of error information by bypassing this formula. And think about the role of this margin of error value that we have already obtained here. Then it will be substituted into the value of e on the left-hand side of this equation. But the right-hand side, and particularly inside of my square root expression, the entire information regarding the sample proportion value is still completely absent. So in that way, we still need to find our p hat value. And here in this information, even though it's not written out directly, but there will be a way to find out what our sample proportion, particularly that came up with this interval. So the way to find out which sample proportion value that produced our interval here, here's how we're doing it. Take account of the fact that this or any other interval has the sample proportion value right in the middle. So being the midpoint of a segment like this, being a midpoint of any distance, then that midpoint value, the standard math to find midpoint value is always, we're going to go 0.7715. This is the high end. And we're going to also consider 0.7485. This is the low end. But the standard math to find midpoint is we are going to add these. So add lower and high end and divide it by 2. We will come up with a value exactly in the middle. So here's low end, here's the high end, adding the 2 and divide by 2. That will come out to the value exactly in the middle. So final calculation comes out to be 0.76 to be exact. And so now, one more time, I'm asking anyone who is viewing this video of mine is to look back at our formal formula to find margin of error. So margin of error, E equals the z sub c multiplied with square root expression. And inside the square root, we have p hat times 1 minus p hat divided by the sample size. And so now if we're looking at this formula as an equation, then algebraically we can rearrange. So this same equation but can be rearranged. The rearranged version of this is going to be z sub c divided by margin of error square and multiply with p hat times 1 minus p hat equals n. So the exact same equation where we used to use that as a formula to calculate margin of error. Here in this problem, we apply that equation and rearranged it algebraically to come up with a different formula. But this formula here is going to be beneficial for us in terms of finding the sample size that we're looking for. Because at this point, margin of error is ready. We already had that ready here. Our p hat being involved in the formula is now ready. And so z sub c is independent with any of these information. As long as we had a known confidence level, we can easily find a z sub c. And once we've had all that pieces of information, then we are ready for the sample size. Now, allow me not to show how I algebraically rearranged this equation. It takes some algebra. It does take some algebra. So it doesn't matter what math classes you learn, but algebra is always here and there among your work. So if you need to clarify how I rearrange these two steps here from the earlier formula to this formula, then you can maybe comment on my video here or contact me in person so that I can clarify. But allow me not to show the clarification steps of the algebra work here. And now for the z sub c. Let's find out what value z sub c is. In this case, our confidence level is being given at 0.99. So first step for anyone, 0.5 plus half of 0.99, or half of our confidence level. So our confidence level here is 0.99 over 2 plus 0.5. We now have an area to the left of our z sub c being 0.995. Recall that we call this the area left, meaning it's the area to the left, completely shaded to the left of this z sub c on the standard normal distribution. And so now the next step here, step number 2, we're finding that z sub c by simply running the INVZ program or any equivalent program that's inverting an area shaded to the left of a z-score to find out which z-score that is. So now when you're using technology for that, and technology will be asking for area left, we are going to provide 0.995. And let's see what kind of a z-score we are getting here by inverting this area. So calculation from my INVZ program shows that the z-score that gives the left area being 0.995 is going to be 0.575 and a lot longer. So on my decimal, on my board here, I'm only going to be using 3 decimals. But in this case, so our final concluded z-score that we're using here is 2.576. So now having margin of error ready, having sample proportion value found, this sample proportion once again is the middle value in our interval that produced our interval. And here's what we just now calculated. This is z sub c that we've already calculated, directly related to the confidence level given here. And so in that case, now our formula to find the sample size is ready. So n, capital N equals, once again the formula was z sub c divided by margin of error square, and we multiplying with p hat times 1 minus p hat. All right, and so now we're looking at 2.576. That's what's substituted for z sub c, divided by 0.0115 substituted in for margin of error, square the quotient. And so you can see that I purposely wrote these, filled down these numbers in the according to the order of operation. So we need to divide first, then that quotient is being squared. And once we're done with squaring that quotient, then we're going to multiply with 0.76, our found sample proportion value. And then we are again going to multiply to 1 minus 0.76. And let's see what this calculation is going to come out. So final calculation comes out to be 9,152.1024 and a lot longer. So we're close to getting a final answer, but let me tell everybody, let me tell anyone who's viewing this video of mine right here, but we cannot take this as the answer to our question. So let me tell you why. Nothing's wrong with the formula, and nothing's wrong with performing the calculations on the calculator. Nothing's wrong with the calculator as well. What happens here is that if we're looking at the meaning of this capital N letter over here, it means it's a sample size, and each sample in our problem here is containing the number of people who are using cell phones, where in our category, we're looking for iPhone users. For short, a sample size is the number of people. So, can people or can a person be cut apart to find only a 0.102 something of that person? We cannot do that. And so my point here is that being sample size, it needs to be a whole value. So that needs to be a whole value. So after I was making that simple joke about we cannot cut a person apart just to get a 0.1024 of that person, then I just want to make clear my point that any sample size needs to be a whole value, a whole number. Plus, I've made earlier argument that when we're estimating, the bigger sample size we use, the better estimate we'll get. So this value, the intention here is that it's the least value so that we can achieve this good estimate. So anywhere above that is good, but don't go lower than this. So now we can formulate two requirements for our sample size. Being a whole value and must be anywhere at least 9152.1024. And so being anywhere at least 91252.1024, that means if we round to a whole value, all of that together here, we need to round. We're going to have to round to the nearest whole value, but above, because you see, and it's perfectly good in this example that we already had a final answer with a very low decimal part, so that if we only round to the nearest whole value without enforcing the other requirements, then a lot of times people might mistakenly round it down to 9152, but remind yourself that what we need here is, yes, the sample size, any sample size needs to be a whole value, and it has to be, according to this problem, it has to be anywhere at least 9152.1024, at least that value. So if we round down to 9152 right here, then it's not at least this value. And so we, in the end, combining the two logics together, sample size needs to be a whole value, n has to be anywhere at least whatever came out from the calculation, including the decimal. Then we need to round to the nearest whole value above. And let's make that so nearest whole value above. And so in that case, our final answer here is easily 9153, even though the decimal here is really small, so nearest whole value should bring you down to 9152, but here we need any number that at least this value or more. So the nearest whole value above this number is 9153, and that's the answer. All right, and so now allow me to make a final note before we close down this example. So I have introduced throughout our work that the sample size, we can find that by doing z sub c divided by the margin of error found directly from the interval given, and the quotient there is being squared, then we multiply with p hat times 1 minus p hat. And I emphasize that we need, after we've got an answer from using this formula, then ensure to round the answer to the nearest, and this is the important understanding that I have to keep it written in capital letters, the nearest whole value above. So quite important, the nearest whole value is one element and being above. It must be above whichever the answer that comes out from this. And so in my lecture, this is about all I introduce. And if anyone who's viewing this video happen to read quite a few textbooks over the web or being sold in the market, then the same formula here, but many textbook authors also have written the same formula as the sample size equals, so all that there is E sub c over margin of error, the quotient square multiplied with p hat times 1 minus p hat. But then the formula that appear in many textbooks have this pair of symbols. And this pair of symbols in the end is actually one symbol being understood as the ceiling function. So I just want anyone who's viewing this video to be aware that. So the same exact formula, but many textbooks have the formula written that's including the ceiling function. So those authors of textbooks out there, they want to indicate that yes, the same work here, after we've got the answer from this formula, we need to round, that's what the ceiling function is for, we need to round the answer to the nearest whole value above. So the reason I'm not writing down this formula, and I don't really have to, and I really do not require anybody of my class, any students in my class, to know this fancy formula. It's just myself that I chose not to use the fancy looking formula like this. The reason is, in the end, this video is intended for a stats course, and this way of using this formula, and particularly this symbol, is mostly used in computer courses. And so it's just a little surprise that right here in our stats course, it has this function, this ceiling function has a little bit of application. And that is the reason why many textbook authors out there use this symbol. But I feel it's unnecessary. And so all you need to remember is that answer of yours, and after so much explanations of mine, that answer, whichever answer you've gotten out of that formula, just simply round your answer to the nearest whole value above. And all that understanding is equivalent to all this. And once again, I will never require any of my students to know this fancier version of the formula.